All right, so what I'm going to be talking about are experiments that we conducted in an indoor air quality chamber to characterize dynamic responses of, in this case, viral challenge agents, specifically T1. So the overall sort of roadmap for this presentation, the objectives really are to quantify these responses in an IAQ chamber. So what I'm going to do is present the IAQ chamber in terms of its geometry and physical characteristics. The experiments that we conducted in numerical simulations as well that were used to characterize the fluence rate field. Some testing that we did using carbon dioxide as an inert tracer. I do have data on ozone and particle dynamics, but I won't present that unless there are questions. It's included in the slide deck, but in the interest of time, I'm not going to present that initially. And then talk about what the challenge agents did, how we measured their dynamic response in these systems. There were two experiments that we conducted, and I'm referring to them as a continuous introduction experiment. That's where the challenge agent, in this case T1, was introduced throughout the entire period of the experiment. And the second one is an experiment that we refer to as decay, which is sort of a mimic of what's suggested by ASHRAE 241, where you introduce the challenge agent for a period of 2 hours to get to nominally a steady state condition. Then you terminate the introduction of the challenge agent and turn on the UV system. And then I'll conclude by presenting information relating to the mathematical model that we just used to describe the behavior of both experiments, and from which we developed estimates of equivalent air change. All right, so here is the IAQ chamber. Its dimensions are listed here. It's got a volume of about 57 cubic meters. It has a dedicated HVAC system, so there's a single inlet and a single outlet. The inlet is along the floor, the outlet is in the ceiling. We used 2 box fans in this room to promote mixing, and I'll come back to that in a few minutes. There is an adjacent room that allows, that is the room from which we introduce the challenge agent, whatever it might be, and it's also the room from which we collect samples. So we basically drilled holes in the wall so that we can inject through one and collect samples through the other. And then lastly, there are 4 optically filtered krypton chloride lamps that were provided by Ushio. Their orientation in the plan view is illustrated here, more or less a uniform distribution across the ceiling of the room. All right, so in terms of characterization of the fluence rate field, there were simulations that were done using visual. Thank you, Holger. So here are 2 illustrations of the results of that simulation using visual. On the left panel illustrates the fluence rate field in a plane that was 45 centimeters down from the ceiling. And the right panel illustrates, using the same color scheme, the fluence rate field at a plane that was 90 centimeters from the ceiling. That's nominally 1.8 meters up from the floor, so basically eye level. All right, so this sort of illustrates the spatial distribution. We do also have information from this simulation to suggest that the room average fluence rate was about 2 microwatts per square centimeter. And then we have information also to describe the minimum and maximum in these 2 planes. And you can see how that translates in terms of an 8-hour dose at these locations. All right, we also conducted experiments to measure the fluence rate field within the system using an approach called spherical actinometry. The basic idea is that we have these little tiny quartz spheres that were produced by our glass shop. They're 1 centimeter in diameter. They were placed in these same 2 planes that I referred to at more or less a uniform distribution across those planes. And at each location, they were suspended from the ceiling using monofilament fishing line. The actinometry involved iodide and iodate, so basically it's a 200 microliter injection into each of these little spheres. We exposed them in this experiment for 3 hours and 45 minutes because we found that that was enough time to get measurable absorbance of the triiodide that's produced in this experiment across all 32 locations. And then we did this so that as a check really of the simulation that was done with visual. All right, so there's a lot of numbers on this page. Let me just sort of orient you to this. The black numbers at each location represent the measurement by spherical actinometry, and the pink, whatever that color is, at each location is the corresponding numerical simulation result. And so, for example, those 2 numbers right there correspond to that location, and likewise for the rest of the locations. So the left panel illustrates the higher plane, 45 centimeters from the ceiling. The right panel illustrates basically the plane at nominally eye levels for somebody nominally my height, 1.8 meters above the floor-ish. All right, and maybe one other thing to point out is that these gray areas here illustrate the locations and approximate size of plexiglass windows that are located around this IAQ chamber. Now that's relevant because the modeling does not account for reflection or refraction, reflection being more important in this situation. And so, for example, reflection down here in this corner where we have two windows is more likely to be relevant than in an area out here. All right, so that accounts for sort of the non-uniformity that was evident in the spherical actinometry, or let's say the non-symmetric behavior that we observed with the spherical actinometry. But generally what we observed was that there was qualitative agreement between the numerical simulation and the measurement by spherical actinometry. It's important to recognize both of these methods have error associated with them, so I'm not going to claim that either of them is correct. But I will say that they do have at least qualitative agreement. One other thing that sort of sticks out with this, and I'm just going to focus on those 2 points right there, whether you're measuring with spherical actinometry or simulating using a numerical model, there are strong gradients in the fluence rate field that are evident in this. That translates to equally strong gradients in local photochemistry or photobiology. So that's, I think, important in terms of understanding the results of any experiment that you conduct in this sort of setting. All right. I mentioned we also looked at these tracer tests that were conducted. So here's an example of a tracer test that was conducted in this chamber. And basically what we did was we introduced carbon dioxide for the first 2 hours of this 4-hour experiment. And then we had a fleet of these little carbon dioxide monitors that we had stationed at various locations, more or less uniformly distributed around the room. What we would expect in a well-mixed space is that first of all, that all of those carbon dioxide concentration profiles would basically fall on top of each other. And there's also a characteristic shape that would show up in this behavior. So we sort of got those results, and so I'm going to say this was sort of a well-mixed space. What I would suggest is that these characteristics do, at least in some respects, mimic a well-mixed space in the sense that the concentration profiles at all of these locations were essentially the same. But there's a notable sort of weirdness that shows up right here that is entirely inconsistent with a well-mixed space. And generally what we observed in this experiment and the other experiments that I'll show you is that the behavior on the ascending part of the curve is less regular than the behavior on the descending part of the curve. I think there's a fluid mechanical explanation for that. Happy to discuss it if you have questions, but nonetheless, that is consistent with what we observed. I'd like to point out also that we do have an anemometer that's located in the supply duct for this room, so we can measure a local velocity. And if we assume that that velocity is representative of all of the air that goes through this inlet duct, then we can use that to calculate a flow rate from which we can calculate air change. And that turns out to be 2¼ air changes per hour. But one of the other benefits of doing the CO2 test is that you can get a perhaps better measure of actual air exchange that takes place within the system. So these are 3 of those sort of exponential decays that showed up from 3 of these CO2 monitors. And if you look at these data, they are in pretty good agreement, and they look like more like 2¾ air changes per hour. So there's some fuzziness in these numbers. I personally would have more confidence in these numbers than that one down in the lower right corner. All right, so we conducted experiments with, we have conducted experiments with both T1 and MS2. I'm going to focus on T1 largely because T1 is better, I think, as a surrogate for the pathogens that we care about. So we're not doing experiments with true pathogens in this lab. So we're using a surrogate, and we're going to use intentionally a surrogate that is slightly conservative relative to the pathogens that we care about, which happen to be, for example, the coronaviruses and influenza viruses. If you were to look in the data at the reported values of the inactivation behavior of those 2 groups of viruses, they more or less fall in that triangular region. So T1, I would argue, is an appropriate conservative challenge agent and much better than MS2, which has been suggested, for example, by ASHRAE. You could argue that, yeah, MS2 is more conservative, but I mean, that argument would be correct, but it also presents some pretty serious problems in terms of translation of the results from the challenge agent to the pathogen that we might be interested in. Okay, I'm going to skip over the safe traces stuff because, again, I don't think that stuff is mature enough to be able to present. All right, so what I want to do is to set the stage in terms of the model that we use to describe the dynamic behavior of this system. So here's a definition sketch to illustrate the behavior of the system. We have many of the characteristics of the system that are really pretty easy to measure, things like volume. We have an estimate of the spatially averaged flow rate. We can come up with a representation of the rate at which the challenge agent is introduced, and we can also measure the volumetric flow rate of introduction of air into the system. So we can, just using basic principles of mass balance, come up with an equation to describe the dynamic behavior of the system, and this is really sort of the central governing equation that we use. It accounts for the effects of endogenous decay, deposition, and the effects of UV, which is really what we're trying to tease out of this experiment. Okay, so if we look at this, sorry, I'm not going to spend too much time on this, but I'm happy to come back to it if you have questions. So this is a description of what I referred to previously as the continuous experiment. So in the continuous experiment for the first 2 hours, we are not using UV, but we are introducing the challenge agent. And so what we'll do is just assign values of 0 to those two parameters. What I did want to point out is this parameter that we're calling alpha 1, which accounts for the effects of physical air exchange, endogenous decay, and deposition. Those are all not only first-order processes, so the time constants are additive, and so we add them. And that parameter turns out to be really the fitting parameter that we apply nonlinear regression to come up with an estimate, or an estimate from an experiment. All right, so the second half of this continuous experiment is one where we turn on UV after 2 hours. And so the equation is, it's the same governing equation, but we can only get rid of that first term on the right-hand side. There's a different value of alpha, and the difference between alpha 2 and alpha 1 is the effect of UV. So the difference between those two parameter estimates then gives us an estimate of the effect of UV, which is what we're looking for from this experiment. Okay, so here's an illustration of data from a continuous experiment. So again, the challenge agent was introduced continuously over the entire 4-hour period of this experiment. The lamps were turned on at t equals 2 hours. So we selected that because in other experiments we get to something that looks like a steady state condition after about 2 hours. But again, on the ascending part of the curve, we have some weirdness that's showing up. I don't have a complete explanation for that, but this shows up in many of the experiments that we conducted, especially recently. So what we did in this experiment is to use the average of the last 4 data points, basically from t equals 1 hour to t equals 2 hours, as representation of the first steady state condition. When we reach that first steady state condition, that's when we turn on the lamps, and then we look really at the decay response that takes place. So that decay response, or the descending portion of the curve, tends to be more regular, and really the error or variability that shows up in this data set, I would say, is sort of characteristic of the microbiological assay that was used in this experiment. So I'm not too bothered by that. I am concerned about this. This method, as I'll demonstrate in a few minutes just by modeling, I think is superior to the decay method, largely because it's much more amenable to, let's say, a wider range of responses than you would get or that would be allowed using the decay method. Anyway, in this situation, as I mentioned before, we have estimates of alpha 2 and alpha 1. The difference between them is then our estimate of the behavior that's attributable to UV, in this case about 1.8 equivalent air changes per hour. Okay, so here is this corresponding math for the decay experiment. Again, I'm not going to go through the gory details of it unless you're really interested, but the bottom line is that for each of these simulations, there's these 2 parameters, alpha 1 and alpha 2. The difference between them gives us a representation of the effect that's attributable to UV, which is what we're looking for. All right, so here is an example of a decay experiment. Again, we see this sort of noisy behavior approaching the first steady state condition. By the way, the first 2 hours of this experiment is nominally the same as the first 2 hours of the second experiment. The difference here is that we turn off the challenge agent introduction and we turn on UV at t equals 2 hours. So then we're just looking at the decay response, and you can see this pretty regular decay. But one of the big disadvantages of this decay method is that we really only have 2 or maybe 3 data points from which to do our regression analysis. So it's a much less robust data set, and pretty much every time you're getting right down to the limit of detection very quickly. It's really just a question of how quickly you get down to that limit of detection. So I think that's a really important limitation of this method, and it needs to be addressed. Okay, there's another experiment that we did was the decay experiment without UV. Now in this case, the value of alpha 1 and alpha 2 should be the same because we're not using UV. So if you consider, if you were to go back to the messy math that I presented a few minutes ago, the difference between alpha 1 and alpha 2 are the same, except that alpha 2 accounts for the effect of UV. If you turn off the UV lamps, then alpha 1 and alpha 2, which describe the dynamic behavior in the first and second parts of this experiment, should be identical. But according to the regression analysis, they weren't. So what we observed was that, I think that's largely attributable to the weirdness that's showing up here, but that's really just sort of arm waving at this point. A different method that we can use to evaluate the effects of UV is to consider only the decay portion of the curve. So if I go back one slide and consider the decay portion of the curve in the presence of UV, in other words, what we're calling alpha 2 for UV, and alpha 2 in the absence of UV, the difference between those two would be another representation of the effect of UV. So in this case, we came out with about 1.1 equivalent error changes. All right, so what I wanted to do then to sort of wrap this up is to compare these methods literally side by side to consider what are their strengths and weaknesses. And I've already alluded to these somewhat. So on the left side is an illustration of a numerical simulation of a well-mixed system following the other assumptions that went along with this model. Some of those assumptions are listed up here. And what I've illustrated is values of what we've called alpha 2 of 5, 15, and 50 inverse hours. The idea is to look at a wide range of operating conditions. Again, as I mentioned before, one of the big strengths of the continuous method is that we have much more, let's say, robust data sets to work with, and we're going to stay above the limit of detection basically throughout the entire experiment, unless we get to extreme conditions. Whereas with the decay experiment, we are very quickly getting down to the limit of detection, and we're really very constrained in terms of the number of data points that we can apply for the regression analysis to come up with the parameter estimates that we're looking for. So again, I think that's an important limitation of this so-called decay method, and it needs, again, it's something that needs to be addressed. All right, so some conclusions and observations. First, the CO2 tracer tests allows us two things, really an assessment of mixing behavior and also an assessment, a quantitative assessment of actual physical air exchange. The spherical actinometry and numerical simulation efforts provide us with reasonable representations of the spatial distribution of radiant energy, in other words, the fluence rate field. They're in qualitative agreement, but there's additional work that's needed to try to resolve the differences between them. The configuration that we used in this system yielded a fairly modest effect of UV, and in fact, because we were somewhere in the vicinity of 1 to 2 equivalent air changes with this system, that makes this really fairly difficult to differentiate from the other effects that are present within the system: physical air exchange, deposition, endogenous decay, that sort of thing. So these methods would be, at least the continuous method, would be easier, I think, to apply for a system that was much more aggressive in terms of the amount of UV that was applied and the number of equivalent air changes that were being applied as well. And that really is sort of, at least as I see it, an inherent advantage of the continuous method. All right, so going forward, what we want to do is to develop these methods to standard, to form basically a standard. And that would include quantitative assessments of fluid mechanics and mixing, some sort of test, whether it's a CO2 or something else, that is used to characterize and quantify the fluid mechanical behavior that's evident in these systems. We also need a quantitative assessment of the spatial distribution of radiant energy so that we can account for it in terms of disinfection efficacy and human exposure. And perhaps most importantly, these tests need to be set up in a way where the results can be translated from the test environment to the application environment. What I'd like to be able to do is to take the results from the IAQ chamber and apply it to a room like this if UV were used and be able to do that accurately. And I don't think we're there yet. We're looking at the incorporation of new challenge agents, whether they're viral or non-living agents. And also, again, as I mentioned, or as I did mention, translation of the test results to other pathogens. And then lastly, we did do some measurements of ozone dynamics and particle dynamics. And I'm happy to show those if there's interest. But I think going forward, one of the things that we need to consider is not just the presence of particles and their size distribution, we also need to consider their composition. But because in terms of the toxicological effects of these particles on humans, it's not just the presence of a particle, it's what's in the particle that's likely to influence the toxicological effect. Okay, I'll thank the sponsors of our work, and I can answer questions.